what I went over the very last lecture. Okay? And so we talked about if you take an olefin, and if you take Br2, by the way, it's gold and white. I just dress colors. So we take an olefin and we go in Br2. And Br2, the olefin is going to attack Br2, giving us these intermediates here that eventually give us a bromonium, and Br2 attacks the bromonium to give us our transbromide. So with olefins, double bonds, this is what happens, right? Br2 adds across double bonds and gives us these dibromides. And as I said on Wednesday, aromatic groups are pi systems. So would a pi system do this? And would an aromatic system do this? And we know the answer is no. So this does not happen. And here's the reason why it doesn't happen. So if we start with a benzene ring, and then we go in Br2 and hypothetically form the bromonium as a double bond, there's one major difference, and that is the energy level of an aromatic system is going to start off significantly lower relatively than the energy level of a non-aromatic double bond. All right, so what this means is the key step. So going from here to here, or here to here, is determined by how fast and how well it happens, determined by the activation energy. Or in other words, activation energy is the difference in energy between the starting material and the transition state to get to the intermediate. So starting, if this is A, and then this is D's energy level, and then going from here to here, the difference between ground state to transition state is activation energy. And so since an aromatic system is so much lower in energy than a double bond, and hence starts at a lower energy relative to a normal double bond, that means that the activation energy, which we give by triangle G, or delta G. So in science, delta means the difference in something. So delta X would be the difference in X if it's a coordinate on the Cartesian plane. So delta G means the difference in energy. Delta G means the difference in a reaction. That's PChem stuff, so you can take PChem, that matters. For my class, it doesn't. But some chemistry majors just hear it before PChem. So the activation energy, or delta G, going from here to here is going to be much lower than the delta G, or activation energy, going from here to here. All right? So that's reason one why this reaction doesn't happen. And by the way, I'm just going to scribble this so you guys in your notes say that this reaction doesn't happen. So that's reason one, this theoretical reaction does not happen. Reason number two, of course, is just you look at the relative energies of the starting material and the product. So for this dibromation across an olefin, the product and starting material are going to be in the same plane of existence when it comes to energy level. So stability-wise, there's not going to be that big of a difference. And so then if you're in a thermodynamic situation, it's not going to go backwards or forwards. It's just going to do the kinetic thing and just stay there depending on how much energy you have in the system. So because A and C are equal in energy, the reaction can go forwards or backwards depending on how you do it. However, for an aromatic system, we start out with P, which is aromatic, and we start out with, and then we go to a product which I call F, and F is not aromatic, right? We broke aromaticity in forming the bromine bond, and that means the energy level of the product F is going to be significantly higher than the starting material. And so what that means is even if this reaction happened, we would get to F, but since most of these reactions we know can be reversible through an E1 type mechanism, so this chemistry is reversible through an E1 type mechanism, since it can go backwards, it will. So you don't lose aromaticity. So even if this did happen, it would just go back to regenerate aromaticity. So the two reasons why we don't add Br2 across an olefin is because, number one, the most important reason is this activation energy is much higher because we start up in the aromatic compound. And then reason two, which is less important, and I'm bringing it up because it's going to explain something I'm going to talk about in 5 minutes much more. Reason two is that the product is much less stable in the starting material, so the equilibrium is just going to lie towards a more stable thing, which in this case is going to be the aromatic product. So this reaction doesn't happen. And if you throw in Br2 to an aromatic compound, as is, nothing will happen. And nothing will happen because its activation energy is too low. However, you can add a catalyst. And the catalyst we'll talk about for bromination of benzene will be FeBr3. So it's an iron with 3 bromines on it. In three dimensions, it's just going to be a planar, trigonal planar molecule. So if you take this molecule, and then you throw in some Br2, what's going to happen is the iron tribromide is going to act as a Lewis acid. So this, I hope, reminds you guys a little bit of the aluminum AlH3 things we talked about when we talked about the reductions. And so usually metals in the same place at the periodic table as iron or aluminum are very good Lewis acids, specifically when they have 3 substituents. And so since this iron only has 3 substituents, we can think of it as a Lewis acid just as we thought AlH3 was a Lewis acid when we were talking about the hydride reductions. And so what actually happens in this case is one of the lone pairs of electrons in the bromine is going to attack the iron. And that is going to give us now a tetrahedral iron species. And so just like boron, when iron has 4 substituents, it now has a minus charge. So it gives us this, where we now have this weird looking bromine-bromine iron bond. The next step is this bromine is just going to fall off. This bromine is going to give the electron it shares in the bromine-bromine bond to this bromine. And what that will give us is going to be bromine plus, and then FeBr4 minus. So what the iron just did was it activated Br2 from acting like Br2 neutral to acting like Br plus. So what's going to be a more reactive electrophile, Br2 or Br plus? Br plus. And so what we just did with this catalyst FeBr3 was we took a electrophilic reagent in Br2 that was not electrophilic enough to react with benzene to making a reagent, Br plus, that is now significantly more reactive than Br2 and is now reactive enough. So then what's going to happen, so FeBr3 and Br minus through this mechanism is going to give us Br plus. And then the aromatic system will attack the Br plus. And so by going from Br2, in this case, to Br plus, we are now the fact we're forming Br plus is going to lower this energy level. So if we're going from Br2 to Br plus, we go from going from B to this energy level to now something that's going to be a little bit lower. Maybe along the lines of here. So using Br plus generated by the catalyst is going to lower our activation energy for this reaction enough so that it happens. So now using FeBr3 allows us to do what we couldn't do before, which is a benzene attack at Br. Let me be consistent. So that gives us an intermediate like this. Okay. And so now you could say, well, now maybe we form Br minus and then Br minus attack this to give us that. But that's not going to happen for two reasons. One, our Br minus isn't existing as Br minus, or Br minus existing as FeBr4. So it's not as good as a nucleophile. But also, more importantly, we lose aromaticity. And I said the second reason this reaction does not happen is because the product is much higher in energy than the starting material. So losing aromaticity is usually not a good thing. So when we're talking about mechanisms, drawing a mechanism that loses aromaticity in the product, probably not going to happen unless you're an enzyme. And enzymes can do it. But enzymes have had a billion years to figure out how to do it. We haven't. So what happens next is actually now an E1 mechanism. So we have a positive charge, and we have a hydrogen adjacent to the positive charge. And this, so it's pretty much set up to an E1 mechanism. And the base for this is going to be our FeBr4 minus. Let me actually draw it bigger for the camera. By the way, a student is going to be videotaping this lecture, and we're going to figure out a way to post each of these lectures on Blackboard.
Oh, wow.
Give us some time. I know I can post videos. I'm not sure if the student can post videos, so we have to figure out if he's just going to email it to me or how we're going to do it. But we'll figure out a way to post the lecture starting today. Hopefully the quality is good, both scientifically and video. So I'm drawing my FeBr4 like this, where it's FeBr3 with one of the bromines sticking out. And then, of course, there's a big minus charge. I'm just drawing this just because it's easier for me to draw. You can do this with FeBr4, it's perfectly okay. And so what's going to happen is an E1 mechanism, where the FeBr4 minus, one of the bromines is going to act as a base, grabbing the proton, and doing our E1 take mechanism. To give us our product. And so instead of adding two bromines across the bond and forming and generating aromaticity, we are instead doing an E1 mechanism and just substituting one hydrogen with the bromine. So this is a general concept, and the concept of chapter 15, which is you do not add, you do not do additions across benzene, you do substitutions. So you replace a hydrogen bond with an R group. And this class of reactions we'll be discussing today all go through a similar mechanism, where we take our electrophile, and we make our electrophile better. We make our electrophile better. And then from our better electrophile, it then attacks to give us a carbocation intermediate, and then we do an E1 mechanism. So I guess for this camera, maybe I'll just write everything here and then move everything to the side. Would that work? So, and so these reactions, where we replace a hydrogen in the aromatic group of the bromine we call electrophilic aromatic substitution. Electrophilic aromatic substitution. And they all occur through a mechanism like this, where we take our electrophile, activate it with some kind of catalyst, do an attack, and then an E1 to regenerate aromaticity. And in a more general term, aromatic group plus an electrophile and a catalyst. And the electrophile and the catalyst will give us an E plus. That the benzene ring will attack to give us our cationic intermediate. Followed by an E1 mechanism to give us the regenerate aromaticity and give us our product. So this is the general electrophilic aromatic substitution mechanism. And I will call it from here on out EAS, EAS for short. And I do play Madden. I'm not age range, so when I say EAS, I think of EA Sports. I remember playing Madden like year 2 when I was in 2nd grade, 3rd grade, whatever. You guys can call me in my backyard playing how old I am. So EAS will do this thing where we replace one hydrogen in your aromatic system with an electrophile. We will discuss several different types of EAS in this lecture, and I'm going to give you a general trend. So starting with a benzene ring, we will discuss halogenation, where we take a halide like bromine, or iodine, or chlorine, or fluorine, and then we take a catalyst, FeX3, so iron with 3 of the halides off of it, through this mechanism I just introduced. And that will give us halobenzenes, so singly halogenated benzenes. I will also talk about a reaction that about 2/3 of you guys did in lab, and that's nitration. So in nitration, you take HNO3, I believe. So you take nitric acid and sulfuric acid, and you replace a CH bond with a carbon nitro bond, with a nitro group. Another thing, so this is reaction 1. This is reaction 2 we'll talk about. And in this case, the electrophilic activation is going to be the reaction of nitric acid with sulfuric acid to give us an electrophile I'll talk about to go here. And let me get my charges right, since that's going to be safe for posterity. So next, the next reaction we'll talk about will be taking SO3 and sulfuric acid. And in this reaction, the product we will get out will be replacing one of the hydrogens now with a sulfur with 2 double bonds to oxygens. and an OH. So halogenation